Hello everyone, and welcome to another video presentation of the University of North Texas Physics Department, courtesy of the Physics Demo Room. Today we'll be talking about is circular motion, in particular uniform circular motion, such that the acceleration or the angular acceleration is not changing with respect to angle. So when we're talking about uniform circular motion, we're talking about an object rotating about a central point. And with that, we have a force that's always pulling in towards the center to be a centripetal force. Now, this centripetal force, we can describe it here on the board as F is equal to the mass of the object times its centripetal acceleration. We usually denote this as A with a subscript of C, to have us distinguish between the linear acceleration and also to distinguish between the angular acceleration, which is usually denoted as alpha. So when we're talking about this centripetal force, well, why is it constant, or why is the acceleration constant? Well, we can think about it in terms of the radius that we have, along with its linear or its tangential velocity. And we can denote it here as A sub c, or the centripetal acceleration, is equal to the velocity, or the tangential velocity, squared all over r. So now that r is the radius. Okay, well, this gives us a little bit of an idea, but we're going to be talking about another demonstration. And we're going to see that if I was to change my radius and nothing else, if I wasn't going to add any force or anything else with that, technically my centripetal acceleration will change, but not my angular acceleration. So that way with this, with the change of r, I can say, well, how does this affect my period of how fast is it going to go around in the circle? And this is where we have the other equation where the centripetal acceleration, if I substitute this in, is equal to 4 pi squared r squared over t squared. And that is actually incorrect. It is just 4 pi squared r over t squared. The reason for that is that v squared is really 4 pi squared r squared over t squared, but we have a division by r from our earlier equation. So this is where the r squared term cancels. This all comes from the value that the velocity is the distance traveled per unit time. In this case, the per unit time of going around one full revolution of a circle is our period denoted as capital T. You'll notice this is very different than lowercase t, because that just tells us the individual time and not the entire period. Now the other part, you might say, well, why is it 4 pi squared r squared? Because this is v squared. Now the actual distance that we travel is the circumference of a circle, which is 2 pi r. So if I was to square 2, square pi, and square r, that's how I get this 4 pi squared r squared term. But remember from before, we divided by r to get the centripetal acceleration, which is why the square term disappears. Now, if we were to look at, say, something a little bit differently and actually have a visualization with this, we can say, well, this is all fine and dandy. This doesn't make any sense to me. So what I have here is that I just have a washer to use for stability. I have a piece of metal that has a hole in it, and it's just a cylindrical tube attached to, and I have this tennis ball that's had a piece of string gone through it and attached to it. And this is all just connected by a string. So what I want to be able to do is show that if I was to set an initial velocity or an initial force of this ball going at a uniform period, but then I change the radius, oh, the period's going to change too. So let me see if I can get this all set up. So now, if I'm going to go with a really long radius or really longer lever arm, so now I'm not going to try to add any force. As you can see, I'm trying to get this as constant as possible as it's revolving around my head. So now if I was to change the length, as you see there, it hit my head, all of a sudden it got faster. As you notice, I only pulled down on the washer. I didn't try to move my arm anymore. So let's try that again. So now I'm going to get this work really, really long. And now watch my hand that's close to my chest. I'm going to now pull it. And the string and the ball rotated faster and faster and faster and faster. I didn't add any extra force. I just now changed the radius, which changed my period. So it didn't affect the force. It didn't affect the mass. It only changed my radius and period. That way the overall force was still constant and was moving with an overall uniform circular motion, which is different than if I was doing this, where all of a sudden, let's say I had it go constantly, and then I would bring it down, then bring it up, or I would slow down and change the force. That would be something along the lines of, if I purposely changed the forces every single time, so that way my acceleration was different, or the rotations was different, that would be a different example of circular motion. But in this case, we were talking about uniform circular motion, that if I change the radius without adding any extra force, the period has to change. So now the final question with this is, how much do they change by? So if I was to change the radius by 1/2, the period would have to change by, I believe, 1/4. That way, because it is going to be, this whole thing has to be, it has to be changed by 1/√2. So if the radius went by 1/2, the period would have to go by 1/√2, because the period squared. So that would be the same thing of, if I was to change the period, it would have to be not exactly directly proportional, but one of them is a squared term. Well, thank you for listening to this video presentation, and have a wonderful day.